All right, so today we're starting the chapter on electric currents. So the last four chapters we talked about electrostatics, where the charges were at rest. And what we were really interested in was finding the electric field everywhere. Okay, so given the charge distribution, you could find the electric field. And the reason we wanted to find the electric field was if you put a test charge anywhere, you know which way it'll feel a force. Okay, so a negative charge feels a force in the opposite direction of the electric field. The force was given by charge times, okay, you saw that. Okay, so we spent 4 chapters studying a static distribution of charges. These charges produced an electric field, and we studied the consequences of that. Okay. What is the next logical step to do?
Start moving them?
Yeah, start moving these guys. Okay, and so now we'll study that. Okay. So, and we'll spend 4 chapters over this. When you start moving them, we call it an electric current. So we'll study the electric current. We'll study some of their properties, and in a couple of 3 chapters, what we'll learn is a moving charge also produces a magnetic field. So I'll draw the simplest case, and if a charge is moving like that, you stick your thumb out like this, and your fingers point in the direction of the magnetic field. So it'll produce magnetic fields like so. Magnetic fields are denoted by B. So draw cylinders around that thing, and it'll produce magnetic field tangent to the cylinder. Okay. So if your thumb is sticking out in the direction of the electric current, your fingers point in the direction of the magnetic field. So moving charges will produce magnetic fields as well. But we'll learn that in a little bit. Okay. So now we are graduating to moving charges. So those are called electric currents, and we'll study that. Then we'll we'll pass currents through various elements in a circuit, and we'll study DC circuits. Okay. And in a later chapter, we'll study AC circuits. Okay. And those 2 chapters will become a whole course for you guys. Okay. Then we'll study how currents produce magnetic fields. So this is just, we'll study magnets first, and then we'll tell you that currents produce magnetic fields. Okay. All right. I'm just showing this to you because you'll see these in your engineering courses. These are called the Maxwell's equations, and they summarize pretty much everything that you study classically, all electromagnetic phenomena. Okay, so I'm just going to tell you a couple of things. What this equation tells you, this is charge density. So this is charges producing magnetic fields. This equation tells you charges produce magnetic fields. All right, and now we're getting ready to study, these are moving charges. This is current density, and current density produces magnetic fields. That's what that equation is telling you. Okay? We'll study this in a couple of chapters, but we'll dedicate 1 chapter to that. Currents produce magnetic fields. What else is this equation telling you? So I just said currents produce magnetic fields, and the form of the equation tells you how they're related, the configuration. For instance, this equation is telling you if you have a current density like this, it produces magnetic fields like that. Okay. But right. So this is also telling you, this equation is also telling you, see, time varying electric fields produce magnetic fields as well. That's an entirely separate chapter as well. Okay, so the point I'm trying to make is we are studying these 4 equations piecemeal, and each piece we're dedicating an entire chapter to. Okay, and so that's what we'll be doing. Now here's another beautiful thing. Okay, what produces electric fields? I said, what did we say? What produces electric fields?
Charged particles.
Charged particles produce electric fields. Okay, so if you have a charged particle, we just said, okay, let's draw another. So simple case. This charged particle produces an electric field around. Yeah. All right, so now let me say there's an electric field in this room. How do you detect the electric field?
Measuring the force experienced by a charged particle.
Exactly. See, a charged particle produces an electric field, and to detect that electric field, you need a charged particle. So whatever produces, and that's what this equation is telling you. So there's a beautiful symmetry to it, okay? All right, so that's what this is telling you. So to detect an electric field, you have to place another charged particle there, okay? And you place a charged particle, if it feels a force, then there's an electric field, and if it doesn't feel a force, there's no electric field, okay? So similarly, so the second part of this equation, so we just saw this part of the equation in the last chapter, okay? The second part of the equation is telling you, you see, we said currents produce magnetic fields. Currents, moving charges produce magnetic fields. So what do you think, how do you detect magnetic fields? You need a moving charge, whatever produces. So you need a moving charge to detect a magnetic field, okay? So there's a nice symmetry to this. Okay, so these are Maxwell's equations in differential equation form. This is the same information in integral equation form, okay? So these are two languages, different languages to say the same thing. English, Spanish, yeah, or whatever you want. Chinese, Japanese, whatever your two favorite languages are, okay? All right, so what are we studying now? Moving charges, okay? So we'll define electric currents, we'll define electric current density, drift speed, Ohm's law, okay, and so on, okay. All right, so let's look at this picture. Here is a battery. What a battery can do is it can produce an electric field in a conductor, okay? So you connect this battery via this wire to this device. What does this device do? What? Go ahead. Don't be shy. Huh? Lights up. What this device does is it converts electrical energy to light, to electromagnetic energy. Okay, so it's a transformer. I mean, you for instance, your heater doesn't do that. Your heater, you pass current through your heater and it converts mostly to light. I mean, mostly to heat. Okay, so your washing machine doesn't do that. Your washing machine, you pass current through the washing machine and it turns stuff. It's an electric motor. Okay, so different devices do different stuff. Okay, so here this guy converts electrical energy to electromagnetic energy. The bulb in your flashlight, it's about 5% efficient. What does that mean, 5% efficient? Okay, this guy is 40% efficient. What does that mean?
That means that 40% of the energy is converted into light,
That's right, that's what that means.
and the other 60% go into like heat.
Right.
Or
Mm-hmm.
maybe it stays in the current even.
No, it gets converted to heat. That yellow light, that yellow bulb, that's 5% efficient. Gotta love it, right? What is an LED bulb? It's 90% efficient. Okay, we got all got to switch to LED bulbs. All right, so well, coming back to this thing, okay, so when you close the switch, what this battery does is it establishes an electric field in this wire. Okay, and in the conductor and in this guy as well, what happens is there are free charges, and what you do is you establish electric fields, and free charges are free electrons. And soon as you establish this electric field, these electrons will start moving in the opposite direction. These electrons start moving, they'll hit special atoms in there, excite those atoms, and when the atoms de-excite, they'll emit light. Okay, so that's what's happening. All right, so now let's just look at it from an electrical perspective. You close the switch, and you see this bulb lights up. And in this diagram, what we've done is, see here, this is the positive terminal, there's a negative terminal, here's the positive terminal. So, okay, historically, we've established that current flow, we say that current flows in this direction, but what really is happening is electrons are flowing in this direction. But, you know, the convention, historical convention is to say that current flows like that. So here you see the current is flowing in this direction. And what that is illustrating is this device doesn't care how the current flows. It lights up equally well. Okay? What happened here? You connected two of these, and you will learn you double the resistance, the current decreased by a factor of half, and the power decreased by a factor of 1/4. You'll learn power dissipated in that device is I square R. R is the resistance of the device. The device had the same resistance. Okay. The resistance of the device is the same, but the current decreased by a factor of 2, and so the power decreased by a factor of 4. You connect two batteries, the current doubled, and now this guy is 4 times as bright as this guy. Yeah. Here, the current is the same, and these guys are equally bright, as bright as that. All right, so what is the difference between these two guys? This is as bright as that. So since there are two of them, the battery is you're going to use up the energy stored in the battery twice as fast. Okay, so that battery is going to run down in half the time. All right, so microscopically, here's what's happening. So here's a metal. I'm not going to draw the positive ions. What happens is each atom gives up two or three electrons, and these electrons, so there's a matrix of positive ions. These electrons are free to move about. Okay, they're like the gas in this room, roughly speaking. So when you connect this to a battery, what the battery does is it establishes an electric field in there. Okay, and so in response to this electric field, these electrons move in the opposite direction. Okay, they start moving in that direction. Now what this is saying is, okay, these electrons without the electric field are moving randomly at room temperature, and they're moving at about 1,000 kilometers a second. These electrons in this piece of metal are moving at 1,000 kilometers a second. They would go from here to Atlanta in 1 second. Except that the motion is random, they bounce around, and so on the average, they go nowhere. Okay? And then you connect this battery, establish this electric field, and on top of that random motion, there's this drift motion. There's an average speed in the direction opposite to the electric field. And that is about 1 millimeter a second. Okay, so it's a fairly complicated motion. 1,000 kilometers a second from here to Atlanta in 1 second. And on top of that, here is this drift speed. Okay, so, and that's what constitutes an electric current. So the electric current is made of that drift speed. Okay, so when electrons move through conductors, their path zigzag and collide with atoms. The speed between collisions is 1,000,000 meters per second, which is 1,000 kilometers a second. In the absence of an electric field, when you don't connect a battery, there's no electric field, and those electrons go nowhere on the average. Okay. And anyway, so that's what this is. This is when you connect a battery and you've established an electric field. There's a drift speed there. Okay, so this is 1,000 kilometers a second, and this speed on the average is about a millimeter a second. Typical values between collisions. So here's the time between these collisions. Each change in direction is the result of a collision. Typical time between collisions is 10 to the minus 14 seconds. Okay, so, and they go about 100 atoms before they collide with it. Okay. And the mean free path is 10 to the minus 8 meters. The size of an atom is about 10 to the minus 10 meters. Okay, so, and in a solid, the atoms are closely packed. All right, anyway, that's the microscopic view. Okay, so here's a battery. This is the electrical symbol for a battery. Here's a device that converts electrical energy to light. Okay, at least some of it to light. All right, so when you connect the battery, it establishes an electric field like that, and then electrons respond. Okay, so when a conductor is connected to a battery, it sets up an electric field inside the conductor, which causes a current to flow. Okay, and the electric field is in this direction, from the positive terminal to the negative terminal. Okay, and electrons flow in the opposite direction. So here's, you've established an electric field inside the conductor, and here is the electrons drifting in the opposite direction. The drift speed is the average speed on top of this random motion. Okay, so the motion is fairly complicated. The drift speed is about 10 to the minus 3 meters would be a millimeter, so it's about 0.2 millimeters, or we'll, just to keep it simple, we'll say it's about a millimeter a second. Okay? So now here's a question for you. If the drift speeds are so slow, why does a light come on as soon as you turn on the switch? Okay, so so here's a battery, and here is a switch, and here is the bulb. Let's say the bulb is a street light or whatever, and you close the switch inside your house, the bulb comes on instantly.
Because there's already some electrons on the wire, the circuit wasn't closed yet, so they couldn't reach their destination.
Well, the electrons.
Isn't it like a river? If you push on some of the electrons, right?
Mm-hmm.
They're going to push into the others, and it's going to push all of them down the line. So it's not just the electrons in the battery.
Mm-hmm.
It's all of the wire as well.
Okay, for the light to light up here, the electrons here have to move and start hitting the atoms to produce light. So here's what happens, okay? When you close the switch, an electric field is established at the speed of light. Okay? And the electrons are responding to the electric field. Okay? So, for instance, so let me reframe this question, okay? So let's say if instead of the bulb, this was the sun. and you turned on the sun by turning on a switch in your house. So let's say you close the switch, the sun was connected by this wire. Would the sun turn on instantly? So when would it turn on?
It's like maybe 8 minutes.
8 minutes, there you go. So now you understood, okay? So in that wire, you establish the electric field at the speed of light, and the electron just responds to the local electric field, okay? So, all right, so that's what's going on. The electron doesn't care who turned on the electric field. All it does is it will respond to a local electric field. And if you want to produce light in that device, those electrons have to move and hit the atoms and excite those atoms to produce light. All right, so here's a conductor, and here's how we define electric currents. Currents are denoted by I, little I or capital I. It's the rate of flow of charge. So you can stand here and measure how much charge flows across this area, and the amount of charge flowing per unit time is the current. Okay. Units are, well, charge is measured in coulombs, time in seconds. Okay. Coulomb per second is the unit for current, and that's called an ampere in honor of Mr. Ampere. Yeah. So here are some typical currents. Okay. In a 100-watt light bulb, see, the current is about 1 ampere. So 1 coulomb of charge is flowing per second. Here's a 10 amp fuse in your washing machines. About 20 amps is the current that flows. When your neurons fire, the current is about a nanoampere. Okay. Here's a scanning tunneling microscope where the current is 10 to the minus 10, 11 amps. Lightning has 10,000 amps. Look at the auroras, have 1,000,000 amps. Okay. This is a fusion reactor facility, and 10 million amps, and so on. Okay. All right. So, if you take a straight copper wire, in a copper wire, so here are the positive ions that are fixed, and it's the negative ions in the electrons that carry the current. Okay. So in metals, it's the negative charges, the electrons that carry currents. You can have an electrolyte. In an electrolyte, there are both. So in an electrolyte, for instance, you can take water and mix sodium chloride in it, mix salt in it, and they will ionize, and both the positive and negative ions will carry current. So if you pass a current through this, positive charges will flow in the direction of the electric field, and negative charges will flow in the opposite direction. So in an electrolyte, both positive and negative charges will carry currents. This is in a semiconductor. There are something called holes. Holes act like positive charges, and they carry current. Okay, so here's another electrolyte. And in a metal, it's mostly it's electrons that carry currents. Okay. So here's a wire, and when a current is passing through this wire, what this equation tells you is N is the free charge density. That's how many free charges there are per unit volume. That's the carrier density. So you guys remember how many air molecules there are in this room? What is a mole? How much is a mole? 6 times 10, so roughly 10 to the 24, and there's about 10,000 moles. So there's about 10,000, 10 to the power 28 air molecules in this room. Okay. N in most metals is of that order, 10 to the power 28 per meter cube. So if you took a meter cube of the metal, the amount of free charges in this metal, free electrons in this metal, is about 10 to the 28. Yeah. So here's something interesting. So let's say there is a current flowing in this. So let me do it. This is a battery. Here is the symbol for a resistor. Okay. So when a current is flowing through this thing, okay, the current is given by the charge density, okay, charge per unit volume. Q is the charge of the carrier. In a metal, the carrier is an electron, so that's the charge of a electron. A is the area of cross section of the wire. V is the drift speed. Okay. So let's say, okay, so here's a 1.45 volt battery and a current is flowing through this. What if I connect a 3 volt battery? What happens to the current? If you double the voltage, what will happen to the current? Okay, so you learn Ohm's law. Ohm's law tells you current is voltage divided by the resistance. Okay? So if you double the voltage, what will happen to the current? The current will double. Okay, so now let's come back to this expression. The current doubled, so let's see what changed here. Does the carrier charge density change? No. Okay. Did the charge of the electron change? Did the area of cross section of the wire change? So how did you double the current? The drift speed doubled. So when you increase the voltage, what happens is you will learn that you increase, when you double the voltage, you double the electric field and the drift speed doubled. So when the electrons had a drift speed of 1 millimeter a second, now it becomes 2 millimeters. So that's what you're changing when you're increasing a current in a wire. Okay? So you're making them go faster. Okay? So that's what that equation tells you. Okay. So we'll define something called current density. Okay. So current is the current flowing through this wire. Current density, we define current density is the current flowing through unit area of the wire. Okay. Current density flowing per unit area. And again, that's also the charge density times the drift velocity. Okay, the reason we define this is because remember, what makes a current flow in this wire? What do you have to do? What do you have to do to make a current flow in the wire? What do you have to establish? You have to establish an electric field. Okay, so okay, it turns out that the current density is proportional to the electric field, and so that's why we define this. Okay, so current density is proportional to the electric field. So current density is, and the proportionality constant is called the conductivity of the material. So let's write this QVD. Okay, so this is the charge density, that's the charge of the carrier. This is the drift velocity, that's the conductivity of the material. This is the electric field. Okay. So, like we said, if you double the voltage, the current doubles. And what happened when you double the voltage, the electric field doubles, and the only thing that gets affected is the drift velocity. Okay, so that's what's going on. We'll go in the lab and we'll crank up the battery. So when you crank up the battery, what are you doing? You're electrons. You're cranking up the electric field in the wire, and you're speeding up the drift velocity. Okay, so that's what's going on. So you see, even though you can't see the electrons, you can push them around. All right, so this is current density is proportional to the electric field. Okay, so you increase the electric field and the current density will increase. And this proportionality constant depends on the material, and it's called the conductivity of the material. Okay, in a lot of practical applications, you want to talk about the resistivity. Okay, so conductivity and resistivity are inversely related. Sigma is conductivity, rho is resistivity. Okay, rho, the same symbol that we use for density. Here it's resistivity. Okay, so we use Smith a lot in physics. Smith for everybody, like in Ireland. Okay, so it turns out that this is Ohm's law. Ohm's law says that current density is proportional to the electric field, except that with the instruments we have in lab, electric fields and current density are hard to measure. What is easy to measure is voltage and currents. Okay, so what we'll do is we'll multiply. So here's a wire. There's the electric field inside the wire. You can't measure that, but what you can measure is, and again, this electric field is constant inside the wire. What you can measure is the voltage between these 2 points. And you guys remember from previous chapters, which way do electric fields point? Does the voltage increase or decrease in the direction? Yeah. So electric fields point in the direction of decreasing voltage. Okay. So the voltage difference between these 2 points, this is at a high voltage, this is low voltage. The difference between these guys is called V, and that's E times L. Okay. The length of the wire. So V is E times L, and so we multiply JL over sigma, and J is I over A. So this quantity is called the resistance of the wire. Okay. And so this is called Ohm's law. The voltage across a wire is equal to the resistance of the wire times the current flowing through this thing. Okay, and these guys are easily measured. You know how to measure voltage across a wire. You know how to measure the current in a wire, and you can measure the resistance of a wire. The multimeter we use in lab, that has all those meters. It can measure the voltage, resistance, and currents. Okay, and this is called Ohm's law. Okay, so Ohm's law says you double the voltage across a wire, the current in that wire will double. Okay. So what is happening microscopically when you double the voltage across the wire? What is happening? When you double the voltage, you're doubling the electric field.
You're doubling the drift speed.
Very good, David. Thank you. All right. So the resistance of a wire depends on the length of the wire, the area of cross-section of the wire, and the conductivity of the material. Okay. So you want to double the resistance, you can double the length of the wire, or decrease the cross-section of the wire by half, okay, and so on. Okay. And this is the conductivity. Rho is the resistivity of the material. So here is the resistivity of the materials, of various materials. Okay. So if you want to make a low resistance wire, you want to choose a low resistivity material. So Here's so in a lot of chips they use gold wiring because they want low resistance and you're not spending too much gold. Okay. Resistance, what resistance does is, what does resistance do?
It slows down the current.
It converts electrical energy to heat. Okay, that's what resistance is, like friction. Okay, so if you don't want to waste your dollars, you want low resistance, but you can't have gold everywhere. All right. So now here's a good diagram to remember sort of what's happening. Okay, so what was this device? Yeah, so it's a device that converts electrical energy to light. Okay, so we use various devices. Okay, what we want is we'll have electrical energy at our disposal, and then we want to convert that to various sorts of energy. What does a Tesla do? It converts electrical energy to kinetic energy. Okay, this guy converted it into light. What does a washing machine do? I'm sorry? Yeah, so it converts it into mechanical energy, just like Tesla. What does a toaster do? It converts it into heat. Okay, so does an oven and so on. Okay. A fan converts it into mechanical energy. Okay. All right. All right, so this is a device. I don't know what it is. It could be a light bulb. It could be a Tesla. It could be whatever the heck it could be. Okay, so it's a device. We'll give it the general term load. Okay, so what is this device?
Battery.
It is a store of electrical energy. Okay, this will supply electrical energy to this device, and this device will do whatever the heck it does. Okay, so that's the load. All right, so what this does is, in a battery, really, it's electrons that move, but let's imagine it's protons that move. Okay, let's say it's positive charges that are moving. Okay, so it has electrical energy, meaning it has electrical potential energy. So what this diagram is telling you is, so you can think this is voltage is potential energy per unit charge. Okay, so that positive charge has potential energy here, and as it passes through this device, it's losing its potential energy. It's losing its electrical energy, and that energy is being converted to whatever it is being converted in the load. That positive charge has lost all its energy here after having gone through the device, and then it's come back home. Now what happened?
Battery puts energy in it.
That's right. So the battery has a store of energy. It's some kind of chemical energy. That chemical energy is used to convert that to electrical potential energy. And that's what keeps happening. So the battery spends some of its chemical energy and lifts it up on the mountain there. And then what? Then it can do that job again. How long can you do that?
Until the battery runs out.
Until the battery runs out its store of chemical energy. That's all. Okay. So when you go buy a battery, what you're doing is you bought a bunch of chemical energy. Later on, we'll tell you when you pay $3 for a battery, you're really buying 10 cents worth of energy. Okay. Okay, these are resistors. Okay, so these guys are resistors. Okay. And we've come up with a way of telling the value of the resistor using these color codes. These bands tell you the value of the resistor. Okay. So you read from this end, from the end where the band is the closest. Okay, see, this end doesn't have any band. So the reading starts from here. Okay. The first two bands give you the first two digits. Okay. So this is brown. Brown is 1. Green is 5. So 1, 5. And then the third band tells you the power of 10 that you multiply with it. Brown is 1, so times 10 to the power 1. So this resistor is 150 ohms. The last band tells you the accuracy of this value. So this is 150 ohms. This is gold up to 5% accuracy. If that band was silver, that would have been up to 10% accuracy. And if there is no band there, then it's up to 20% accuracy. Okay, so that band tells you how much money you spent on the resistor. Okay, so again, these bands tell you the value of the resistor. So let's figure this guy out. That's red. Red is 2. Black is 0. And then brown is 1. So that's 200 ohms. Okay, so this is 150 ohms. That's 200 ohms. Okay. All right, so you'll learn this is a capacitor, and I think this might be a diode. I'm not sure about that. But anyway, this is a capacitor. This is a transistor, it looks like. All right, so resistors are commonly made from carbon inside a plastic cover with 2 wires sticking out. Okay. So the value is indicated by those bands. All right, so here is a simple circuit. Here is the load. Here's the battery. The battery is a store of electrical energy or chemical energy. Okay. So what this does is the battery delivers energy to this device. Okay. Power is the rate at which energy is delivered to this device. Okay. And power is voltage times the current flowing through this. Okay. So that's the rate at which the battery delivers power, and that's the rate at which power is delivered to the load. So power is V times I. So the rate at which energy is being delivered is the voltage across this times the current flowing through it, or I square R, or V square R, voltage across this, and so on. Okay, so power is one of these 3 formulas. Again, V I square R, V square. And you can go from any one of those formula to any other using the Ohm's law. V equal to IR. Okay, so that's how they're all related. Energy delivered by the source to the load is converted to heat, light, motion, or whatever. Okay, so when you buy a Tesla or whatever, do you guys know how you're buying it? You're buying it by the size of the battery, essentially. 53 kilowatt hour, 85 kilowatt hour. Okay, so this tells you the size of the battery. You go buy a battery size, and they give you 4 wheels with it. Okay, and the size of the battery determines what your range is. Okay. All right, so here's a. Okay, so Okay, now everything is set up where here's Hoover Dam and power gets to you from Hoover Dam to your house. Okay, so the power delivered is the voltage times I. You can write it like that, or it can be written as I square R. So let's write it like that. So the power delivered is I, the current flowing. So here's Hoover Dam, there's the transmission line, there's your house, and that. Okay. So the power delivered is I square times R, the resistance of the transmission line, and R is the load that's you're using in your house. Okay, so this is the power being delivered to you. What is happening to this guy? What is this guy? That's the resistance of this transmission line. What is this transmission line doing? Just converting it into heat. So this is wasted energy. It's like you're transporting water in a bucket from the well to your house, and that's the holes in your bucket. What do you want to do with the holes? You want the holes to be as small as possible. Okay? So you want to minimize this loss. Okay, look at this expression. This loss, the resistance, okay, so Hoover Dam is about 2,000 miles away. You got to buy 2,000 miles of wire. You can buy copper wire, but that's very expensive. What do you want to do? You want to buy cheap wire. Okay? And cheap wire it has higher resistance, but anyway, this you can't change. If you want to minimize this power loss, what you want to do is you want to transmit power at a very low current. Because if the current size is half as much, the power loss is 1/4 as much. So you want to transmit power at low currents. Well, you're transmitting power. If you want to transmit power at low currents, you want to transmit it at high voltage. Okay, so low current, high voltage. That's why power transmission happens at high voltage. Here in the US, we transmit power at about 750,000 volts. What happened, fellas?
There's a job fair in the student center.
Okay. You guys missed out on pizza and donuts. I'm just kidding. So to minimize power loss, we transmit power at high voltage. Okay. So, and of course, you don't want 80,000 volts coming into your house. So what do? You have step up and step down transformers. You step up the voltage here and you step down the voltage there. Okay. In the US, we lose about so you can major in electrical engineering and power transmission and all that can be a specialization. In the US, we lose about 6% of the electricity in transmission. Yeah. So here are diodes are devices that are one-way gates. You see, here's a light bulb, and when the positive terminal is connected to this end of the diode, it lets current through. When the negative terminal is connected to that end of the diode, it shuts down the current. It only lets current pass through this way, okay? It doesn't let current pass through this way. So a diode is a one-way gate. Right, so So this gate actually opens if you apply a voltage of 0.7 volts or above. If you apply a voltage of 0.5 volts, the gate won't open. Okay, and that's what this graph is showing you. So the diode, see, this is current versus voltage. When you apply a voltage of 0.7 volts, the gate has opened. Okay, you take an ordinary piece of wire, the way the current responds is you increase the voltage and the current in a copper wire increases with voltage. Okay, so if the current response is linear with voltage, that is called an ohmic device. So an ordinary piece of wire is an ohmic wire. Any device that does not respond linearly to voltage, that's called a non-ohmic device. So those are just generic terms. A diode is a non-ohmic device. Transistor is a non-ohmic device, and all those kinds of stuff. Okay. We'll talk about thermistors in a second. Those are non-ohmic devices and stuff like that. Okay. Oh, so here we go. Here's a thermistor. So let's read this. A thermistor is a semiconductor whose resistance depends strongly on temperature. Okay. So remember, so here's current, voltage, and resistor. Okay, so current is voltage divided by resistance. Okay, so a thermistor, okay. All right, before we do this, let's go back to a thermometer. So you'll understand the significance of this. How does a thermometer work? You guys have used thermometers. How does it work?
So traditional ones like mercury ones?
What?
Like mercury ones? Or
Yeah, mercury ones.
mercury, because temperature and pressure affect like freezing points. If the mercury expands at high temperatures, it will go up the meter to a spot.
Yep. So you have a bunch of mercury. If you heat the mercury, what happens to the mercury? It expands. Its volume increases. Okay, and its volume is proxy for temperature. Okay, so you have to calibrate it. You measure this volume. This is the volume of mercury at 0 degrees Celsius, and this is the volume at 100 degrees Celsius. And if the volume is measured to be that's 50 degrees. Okay, so the volume is proxy for temperature. Does the volume increase much for mercury? No, it doesn't increase much. So what do you do? So what you do is, so you have a mercury bulb, and so you force the liquid through a very thin tube because the volume doesn't increase much, and so now you can calibrate it. Okay, but volume is proxy for temperature. Okay, so any device, so whenever you're measuring anything, temperature, anything, some physical property is changing, and you're using that as proxy for temperature. All right, so you're always looking for stuff like that. Look at this guy. This is the resistance of a copper wire as temperature changes. The resistance is not changing much at all. See, it's going from 1 ohm to 1.2 ohms. This resistance is not a good proxy for temperature. Here's a device, here's a material whose resistance is changing by 1,000 ohms over this temperature range. This is one hell of a material for its resistance is a good proxy for temperature. Okay? So if its temperature reduces, you connect a 5-volt battery, temperature reduces, the current changes tremendously. And so current will be proxy for temperature. You guys remember those strips? Nowadays they don't use those, but There used to be strips that you could put on your forehead. You remember that? You're not that old. But anyway, okay, so nowadays those electromagnetic things are cheap enough but back in the day you could have those strips and that would make, so that's what this was. Okay, you put a material whose resistance changed dramatically with temperature, okay? So these guys are semiconducting devices whose resistance depends strongly on temperature. So as you're increasing temperature, what is happening is you're increasing carrier density. And as the carrier density increases, the resistance falls. Okay, so that's what's happening. So thermistors can be used to measure temperature. Yeah. So for most conductors, for copper wires and stuff like that, you see this as temperature increases, resistivity, temperature increases, resistivity increases, resistance increases. Why do you think resistance increases in a copper wire when you increase temperature? I mean, very good, David. So resistance is caused by you bumping into atoms, and you're bumping into atoms more often. Okay? So that's why resistance increases. Okay, and as resistance increases, then you're converting electrical energy to heat faster. Okay? All right, so as temperature decreases, resistance decreases. For all metals, there is, even at absolute zero, there's residual resistivity. Okay? For semiconductors, as temperature increases, the resistance decreased. Why did that resistance decrease here?
Gaining more conductors.
There you go. So you are colliding more often, except that now you're increasing the charge carriers, okay? So let's say it's like saying that you have more postmen now and mail gets delivered faster, okay?
It's like saying the area gets bigger.
Yeah, you could say that. But you're increasing carriers okay? Look at this guy. So here's a material. You decrease the temperature and the resistance at this critical temperature went to zero. Not a finite value. Zero. Well, what does that mean? Okay, what this means is the following. So let's say here was this material and you start a current flowing through it and then reduce its temperature below this value, and then you can remove the battery and the current will keep flowing through it. Because the resistance is zero. It's a frictionless surface. You get the current flowing and it'll keep flowing forever. And they've tested this. So they've gotten a current flowing in a ring and it hasn't decayed for tens of years. That's a superconductor. In a copper wire, you get an electron moving, well, it bumps into atoms and then stops. And so you have to keep pushing it. You have to keep the battery connected. So what needs to happen for the current to keep flowing? What stopped it? Bouncing into atoms. So if you don't bounce into atoms, then you can keep flowing. So in a superconductor, it's gotten into a quantum state where it misses everything. Amazing. So it happens for materials below a critical temperature. Okay? And this is called the superconducting transition temperature. So superconductivity was first discovered in mercury in 1911. This is very cold though. Okay, you need liquid helium for that. Okay. So in 1911, it was discovered. Okay. Now, so what we have been doing is, ever since that, we've been looking for materials that will become superconducting at higher and higher temperatures. Okay. Because we can use, when you go get an MRI done, you know the difference between an expensive MRI and a cheap MRI? More money. So an expensive MRI uses a stronger magnetic field, which gives you a better resolution. Okay, so and they all use superconductors. Okay, so what produces magnetic fields? What produces? Currents produce magnetic fields. See, Carson was listening. Okay. Currents produce magnetic fields. And, if you have a superconductor, then you can pass current without losing much money. You remember? So we've been in the search for higher and higher temperature superconductors. Okay. So this was 1911, and look at this. For 70 years, all we went was from 4 to 30 degree Kelvin. We were getting nowhere. And then suddenly in the 80s, we started looking at materials that we never thought would become superconducting. Somebody said, what the heck? And you started finding high temperature superconductors. The critical temperature thing to pass was liquid nitrogen temperature, which is 77 degree Kelvin. If you pass that, then suddenly stuff becomes cheaper. Okay, and we passed that plenty. Okay, so when you go get an MRI machine, they use superconducting wires where only liquid nitrogen has to be used. Okay. So within the past, of course, we are greedy. Now we want room temperature superconductors. We don't want to spend any money. All right, so here's a superconducting magnet, and here's a magnet that is floating on it. Okay, so you guys have to watch this little video because it is very cool.
Zaxby's just dropped a whole new line of dry rubs, and they're not playing around. Who's got the sauce?
Zaxby's.
Watching the art, the artistry, it was breathtaking.
One doesn't have to be a passionate fan of model trains to be fascinated by the way this steam engine looks. Hovering a few millimeters over the rails, it goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen, so cold that humidity condenses on it.
All right. It's on
the core of this magnetic levitation train is a superconducting material which conducts electric current without any resistance at temperatures below minus 183 degrees Celsius. In this state, it's able to trap magnetic fields. The resulting magnetic forces cause not only the levitation, but precision control above the rail, which is made of conventional magnetic material.
Okay, so that's a maglev train.
An impressive experiment is designed to
what we do is what happens in a maglev train is you guys have all played air hockey. What is the idea of air hockey?
You use air as a cushion to lower the friction.
That's right. Okay, so there is the puck that's riding on a layer of air, and a very little force will push that thing. So the idea is the same, except that you don't want to do with a train, with a train. Okay, so how the heck do you do with a train? Well, you have tracks with magnets, and then you have a train, and what you do is you have a superconducting magnet in the train, and now this will float, and you can push this guy, and it'll go all the way to DC. Okay. So that's the idea, and there have been functional trains in Shanghai since 2014 or 2004 or something like that. Okay. All right, that's it for this lecture.